Good evening, all. I was hoping to take a few moments of your time, try to discuss the pulmonary edema that several of you addressed last evening as we were talking about botulism toxin. And you brought up the idea of pulmonary edema and its relationship to the COVID-19 virus and how it affects then respiratory gas exchange in the lungs. To do that, let's go back to the histology of our normal lung tissue for just a moment and take a look at the players for this evening's discussion. It would be the alveoli themselves, right? The alveoli here. Now I can't, as I do in class, manipulate the microscope up here and increase magnification. I don't believe. No, I can, right? But not like the amount that I can at school with you. But in here are our alveoli. And sitting next to the alveoli are going to be some blood vessels. And specifically, the blood vessels we're interested in this evening are going to be capillaries, alveoli capillaries, that are going to sit juxtaposed right up to these alveoli air sacs. And that is going to be the site at which we're going to get our oxygen and carbon dioxide exchange. And the other players are going to be, well, we have two, our primary pneumocysts and our secondary pneumocysts, or type 1 and type 2 pneumocysts, respectively. Type 1 are going to be involved in this gas exchange. They're a very thin endothelial cell, squamous cell, through which the gas exchange can take place. And the type 2 pneumocysts are specialized for the production of a molecule that's called surfactant, which we'll see in a few moments its particular role in our story. So if you would, with me, see if we can go back down in magnification and now screen down. This was the pictorial representation, an artist's rendering of our type 2 pneumocyst in its relationship to the alveoli airspace, right, the alveoli airspace, and here sits our capillary lumen. So this is the space through which we have to go from alveoli air carrying oxygen and diffuse this through the basement membrane, through the extracellular matrix, and then finally into the lumen of the capillary, into the area where red blood cells will be flowing. And we can then take gas exchange, oxygen being picked up by the erythrocytes, carbon dioxide being released in the blood plasma, and that is going to return again back through that extracellular matrix, through the basement membrane, through the membrane of the alveoli's type 1 epithelium, and then released in our next exhaling carbon dioxide. Down here, these type 2 pneumocysts have kind of an interesting job. If you've ever taken saran wrap and wrinkled it up, or inadvertently wrinkled it up, and then try, especially on a warm, humid day, to then pull that back apart, we usually end up just taking that piece of saran wrap and throwing it out. Well, we can't do that with our alveoli. They're very thin membrane, very thin walls. When they come together, they would like to stick, and they do in some types of diseases. If you ever heard of cystic fibrosis, that's a very sticky alveoli membrane. We don't want that. The surfactant prevents that from occurring, primarily inside of our alveoli when they open and close in response to tidal volumes of air. They are also, unfortunately, the primary target for the SARS-CoV-19 virus. And if you recall, it's the receptor, the ACE2 receptor, that is on these epithelial cells that the COVID-19 actually hijacks. And if you go back and take a look at that, these are the S proteins. Those are the docs that want to hijack that ACE2 receptor that's on our on our secondary pneumocysts. Now, what happens when that occurs? Well, it's a rather long series of reactions, and full disclosure, we haven't been able to show in papers that all the details that I'm going to be giving tonight do indeed occur. So when I talk of certain modulators and certain molecules, I'm using other viruses that are similar to show this pulmonary edema. But I can't say with certainty that it's these particular modulators, cytokines, inflammatory molecules and markers that are actually being stimulated by this particular virus. But we do know them to be very often stimulated by this class of viruses. So let's begin. Once the COVID-19 finds its target, it internalizes. We've already spoke of that. It takes its genome, and as all good viruses do, the first thing it's going to do is it's going to copy more of its brethren. 5' to 3' end with a cap of positive strand plus stranded RNA, like a messenger RNA, goes in and hijacks all the ribosomes inside our pneumocysts. And they start to produce, for discussion tonight, we're only going to concentrate on one group of proteins, and that's the S proteins. It all is going to be made into specialized molecules for assembling coat proteins. But S1 and S2 we've talked about previously, and that's making up the spikes, the coats itself. It also takes and unpacks the Rep1A and Rep1B genes, and there makes it into the proteins that is a an RNA dependent RNA polymerase. And it will then copy with rather good fidelity that piece of messenger RNA. There is the ability, since it's single-stranded messenger RNA, for there to be mutations here, and that does give the virus its variety when you begin to look for its serotypes, but we'll leave that alone for now. So now I have the ability to make coat proteins, and I have the ability to make more core virus RNA. These secondary pneumocysts very quickly are overwhelmed, and the cells die, necrose. And as necrosis begins, there is going to be the release of inflammatory markers from these cells. Markers that are going to stimulate macrophages to be called in for an acute inflammatory reaction. If you recall, acute reactions are going to be primarily mediated by the macrophage and the polymorphic nuclear cells. Usually we refer to those as the neutrophils. So macrophages and neutrophils now are going to be called into action. And this is good. It's a positive thing to allow for our body to recognize that we have been insulted by the virus. But it does lead to some complications that we'll see here. So let's say we have these macrophages, and they're sitting, and I'm going to change now the view, so please give me just a moment here. Still haven't gotten this down very quickly, unfortunately. To our other diagram. I have enclosed this diagram on your Google Classroom. So the macrophage now are activated, and the macrophage begin a cascade of reactions. For tonight, three molecules in this cascade. One of these is going to be tumor necrosis factor, necrotic factor, alpha, TNF, amongst friends, and interleukin-2 and interleukin-6. Now, the interleukin molecules are modulators that will tell other systems, in our case here, the capillaries, to increase their capillary permeability. And that's the part that we want to look in. They carry out an entire cascade of reactions, and I don't want to give you the idea that it's a very simple cascade. It can get very complicated, especially as you get into the different types of interleukins and the steps that they modulate in this inflammatory reaction. The ones tonight we would like to talk about are capillary permeability, vasodilation. So let's look at those. So the idea of increased capillary permeability, let's look at that one first. And this has to do with the endothelial cells of the smooth muscle lining, and the smooth muscle lining, I should say, the endothelial cells in the smooth muscle lining blood vessels. And it's the endothelial cells in response to tumor necrosing factor that will shrink. The cell size literally gets smaller. And with this, the space becomes open between cells. What happens is that the serum in the capillaries, the blood serum and its associated proteins, begins to leak out into this space. And with that, as the proteins leave, water follows it. It's a simple diffusion issue. So water begins to follow this protein, and we literally flood the alveoli. We flood the air spaces now with fluid. This is referred to as your pulmonary edema, and it's one of the major events that initiates the early onsets of the ARDS patients' complications.